initial value problem using Picard's methods, Taylor series method, Runge-Kutta method, Euler's method. Now we learn how to solve if we have a system of first order initial value problem, like if we have two differential equation in first order with two dependent variable and one independent variable. So suppose we have a like in this case, like when we are saying we are learning first order initial system of first order initial value problem, it means that we can solve like a second order differential or third order, fourth order by breaking them into a system of first order initial value problem. So for example, like this thing we have already done in earlier classes also. So, like if this is the second order differential equation given to us, so equation 4.52, and with these are the initial condition y of x naught equals to b naught and y dash of x naught equals to b1. Then we assume that one variable named as u1 equals to y, and then we calculate u1 dash, and that is equals to y1 dash, and the y1 dash we assume another variable u2. So one more time differentiation of y dash will be equals to u2 dash, like this you can see here. So the first equation is like u1 dash equals to u2 with initial condition u1 x naught equals to b naught, as this one is given here, y of x naught equals to b naught and y1 y equals to u1. So it is like this. Then we have u2 dash equals to y double dash, and then we divide by this a naught and take this part to the right of 4.52 equation, and then after taking this to the right and then dividing by this a naught x, we will get this expression. And then here we replace this y by u1 and this y dash by u2, and then we have this. And then this equation or this condition, initial condition y dash of x naught, as y dash of x is equals to u naught, so we replace this by here u2 of x naught, and that one is equals to b1. So it is like this one, y dash of x naught equals to b1. So you can see that from second order differential equation, we have obtained two first order equation in two variable. One is u1, another one is u2. So now that is we are having with us system of first order equations with initial conditions. These are, or you can say these are the initial conditions. This one and this one. So it means that if you have like a third order initial value problem or fourth order initial value problem, so now you have two equation in two variable u1 u2. If you have third order initial value problem, you have three equation in three variable, and then you can say it's a three equation in three variable, still it's a system of first order initial value problem. Then we can write this into a matrix form also, like u1 u2 dash. So here this dash is actually derivative, not transpose. So this dash operator will individually go to every entry of this matrix, column matrix u1 u2. So it means it's a u1 dash and u2 dash entry, and then here we have u2, so this is u2, and the whole thing this up to here we have assumed as f2, and then this is the initial condition where f2 x u1 u2 is given by this. So in general, we have system of equation like instead of having u1, u2 new variable, maybe the problem given to you is already a system of first order differential equations. So you will have this kind of you can represent them in the form of this matrix equation where this y1 y2 dash matrix is this one, and then this f is this and b is this one, b not a b1 transpose, this was f1 f2 transpose, and then we write y dash equals to f, y dash equals to fxy. Here this bold y is actually this matrix transpose, or this matrix, and the initial condition is y of x naught. Y of x naught means this matrix, y of x naught having first entry y1 x naught, second entry y2 x naught, and these are the b matrix. B matrix having first entry b naught and second entry b1. So we learned this we use Taylor series method to solve the system of first order differential equation. So suppose you have this as a Taylor series method of order p. Order p means that you have the sorry, order p means you consider the Taylor series expansion up to h raised to power p and neglecting other terms, or you say that this kind of error you can neglect. So if you are considering h raised to power p, all terms up to h raised to power p, then this method is known as Taylor series method of order p. And then this is the way they have represented in this yik here, y1ik, and then it is representing the k minus 1 time differentiation of f1x y1 comma y2 with respect to x, and similarly y2k is k minus 1 time differentiation of f2 x y1 comma y2 and then you have this kind of approximations. So like this is actually this here, like you can see, if k equal to p, then it is this one, then k equal to 2, it is this one, k equal to 1, it is this one, and similarly for y2 can you can also have. And then we have this we can use this Runge-Kutta method of fourth order to find the solution of system of initial value problem. So this is the method is known to us here, like instead of earlier, instead of having this bold y, we have normal or y. So bold y means it's now in its matrix form. So like yi plus 1 equals to yi plus 1 by 6 k1 plus 2 k2 plus 2 k3 plus k4, and this k1 is here having this k11 and k22. So these are the entry of the k1 matrix, bold face k1 matrix. Similarly, k2 matrix having entry k12, k22, k3 is having k13, k23, and k4 is having k14 and k24. So now how this we will get, like if we are having at nth step, so k and 1. So k and 1 is like h fn xi, y1i and y2i. So if you remember, like K1 earlier is also like H of F x naught y naught. So instead of this, here we are having, actually they are taking I as a naught, or they are taking, like they are calculating I y at I plus 1, having y value at I. So here you can also have this I if you are calculating value of I plus 1. So now since here we are having two variable, one is y1, another one is y2. So this one is like y1 at I point, and y2 is also at I point. Here y1 and y2 are the dependent variable, and I means that at xi. This index I means at xi. Then you require this kn2. So for kn2, it's like h of f, and then you know that it is x naught plus h by 2, and y11 k11 by 2. K11 is the first entry, this one, and then k21 by 2 in y2 variable, because the changes in y2 are related to k21. So k21 by 2. Then in the kn3, kn3 like xi plus h by 2, yi plus 1 by 2, k12, and y2 plus k1 by 2, k22. So that means these two values we are using. And then this k and 4, like h of f xi plus h y naught plus k13, and y2 I k23, like these values we are using 1 3 and 2 3 to get these values k3 and k4. Like from these we are getting this one, and from this we are getting this one, and now from this we will get k4 using this formula. And then the first variable value at the next point, like y1 variable value at the point xi plus 1 is given by y1 at I 1 by 6 k11 plus 2 k12 plus 2 k13 plus k14. So here the first index you see, it is corresponding to the variable y1, and the remaining same thing as the when we have one variable, one dependent variable and one independent variable equation. There we have 1 by 6 k1 plus 2 k2 plus 2 k3 plus k4. So instead of that, because here we have two dependent variable y1 and y2, so here we have reserved the first index of k for y1, y1 dependent variable, and similarly for the y2 dependent variable we have k21, k22, k23. It means the first index here is reserved for y2 dependent variable, and the rest of the things are same, k1, 2, k2, 2, k3, and 2, k4. And then if we have like representing the variable in terms of u and v, y1 is u and y2 is v. So these equation is transformed into this one. So we solve this one problem, solve the initial value problem. So here you can see that here we are having system of initial value problem, like we have two dependent variable u and v, and we have one dependent variable, it can be x or t, anything, and these are the initial condition is given to us, like u naught equals to 0 and v naught equals to 0.5, and we have to take this h equals to 0.2. So we have the value of u0 v0, and we have to find the value of u 0.2 u 0, sorry, u 0.4 and v 0.2 and v 0.4. So these values we have to find, because we have to find the solution on this interval 0 to 0.4. For 0 we know the values, and we have to use Runge-Kutta fourth order method. So first we identify what is x naught. Obviously this is 0 is given, so this is x naught, and u naught is 0 is given, so it is u naught, and this is v naught, it means v naught. So we have x naught, u naught, v naught. Now we calculate k11. So here I told you that 1 is corresponding to the first variable. So it means like we have to identify like u dash equals to this is the equation f on x u v, and v dash equals to f2 x u. So these two functions we have to identify from this our initial value problem. So here you can see this is actually f1 xuv, that is minus 3u plus 2v. And then to identify what is f2, because earlier in we identify what is xy, but here we have two variables u and v. So and for u we have f1 xuv, and for v we have f2 xuv, and here f2 is 3u minus 4v. So to calculate k11, that is we are calculating for u, because first index is 1, and we are calculating the value of k1, and that one, if you remember, it is actually earlier h of f x naught y naught. Since here we have two dependent variable u naught and v naught, so it is h of f1 y f1, because it is for u1. The first index is 1 here. So k11 h of f1 x u naught and f1 of x naught comma u naught comma v naught, and then we know the value of x naught is 0, u naught is 0, and v naught is 0.5. So we substitute in this equation. So if I substitute in this equation, x naught equals to 0, u naught equals to 0, and v naught equals to 0.5. So actually they have directly written the definition of f1 x naught comma u naught v naught directly in this definition. So it is minus 3 u naught plus 2 v naught from here, and then they have substituted the value. U naught is 0 and v naught is 0.5. After simplification, this is the value of k1, or we say that k11 for u. Now it is k2, so it is first index here for this here, this first index k2. As I have already told you, so here k2 is actually corresponding to the variable v. So here we have another function which is correspond to v is f2. And you have already known the one side here one term, and so f2 x naught y naught, and 1 is actually here stands for this. So the second one, like it is actually we are calculating the k1. If we are comparing this over with the single initial value problem, so we are calculating k1 for u and v. For u it is k11, for v it is k21. So what is the definition of f2 x naught y naught x naught u naught v naught? It is like 3u minus 4v naught, like this one, and then you have to substitute the value of u naught is 0, v naught is this, so this is the value, and finally minus 0.4. Now again you have to calculate this for K21 because in this Runge-Kutta method we require this K11 we have already obtained, but these three values still need to find. So like K12, if you remember the case of first like once initial value problem, so there you calculate f2 like h of x naught plus h by 2 plus y naught plus k1 by 2, but here k1 is k11 and there are two dependent variable, one is u, another is v, so you require like f1 x naught plus h by 2 comma u naught plus k11 by 2 plus v naught plus k2 by 2. What is the difference between SPR and Raman? Anyone knows Raman's system? We will start this mathematical equation is so heavy, so I will start from here. So let's start some physical meaning of what is the implication. So of and then we substitute the value of k11 is 0.2, 0.2 by 2 is actually 0.1, and similarly k21 is minus 0.4, it is like minus 0.2. So finally you have these values, and after simplification you have these values, and then you use the definition of then you use the definition of this this definition. If you use, you will have this minus 3 point into 0.1 plus 2 into 0.3, and after simplification you have 0.6. So this is k12, and then you require like a value of this k22 also. So here again we have this. So if you remember the like for one initial value problem, again this is the same kind of formula. Instead we have two dependent variable u and v. If you, so we have like and this is for because now we are calculating for here we are calculating for u, and now we are calculating for v. So k22 is like h of f2 x naught plus h by 2 plus comma u naught plus k11 by 2 plus v naught plus k21 by 2, and these are the value for k11 and k21. So you substitute all these, and then you have to use the definition of f2 x uv, and then you will get this as a minus 0.18. Then you have to calculate u for k13 is required. So you have here f1 and x naught plus h by 2 u naught plus k12. Now these two values are required, this and this. V naught plus 1 by 2 k22, and then it is 0.1, it is 0.03, and 5 minus 0.09, and after simplification you have, and then you substitute the definition of f1, you have this one. Then you require k23, and then again you do the same thing, you will get this, and then here again we require this k14 and k24. So it is for u and it is for v. So here you have f1, and here you can see that 1 3 and 2 3. It means we are using this. So the formula is same, but you have to taken care of that. Here we have two variables u and v. So accordingly it is updated, and then you have substitute all these value, and you will get the k14 and k24 also. So this is k24 and it is k14, and then you know that u1 is u0, that is 1 by 6 k11 k12. So here you can see that one index on the first index is 1. So because we are calculating for updated value for u, and then we substituted all these value. After simplification, we have this as a u 0.2. Similarly, to calculate we use like first index should be 2, and then we have the value of v also. So we have run one iteration, and now we use one more iteration to get the value of y at 0.2. So in the same way you can do, but now x naught is wherever is x naught in the earlier, it is replaced by x1, and wherever is u naught, it is replaced by u1, and wherever is this wherever this u naught, then it is u1, and then the formula will change like this, like u equal for k11 h f1 x1 u1 v1, and then k21 f2 x1 u1 v1, and then you have k11 k21, and then k12 like x1 plus h by 2, u1 plus 1 by 2 k11, and v1 plus 1 by 2 k21, and after simplification you have this kind of values, and after all doing all this you will get the value of u 0.4 and v 0.4. So then we have another example. Compute the approximation of y 0.4 and y dash 0.4 for the initial value problem. For the initial value problem, y double dash equals plus 4y equals to cos t, where y0 is 1 and y dash 0 is 0. So like here it is a second order differential equation is given to you with the initial condition y0 equals to 1 and y dash 0 equal to 0. And the step length is this one. If the exact solution is given by this, find the magnitudes of errors. So here like we have to use fourth order Taylor series method as well as fourth order Runge-Kutta method also. And the step size h is 0.2. So the first job in this kind of problem to reduce this into a system of first order equations. So you assume like u equals to y. So this is your u variable. So your one equation is u dash equals to v, because if you differentiate it v, so you say like they have written y dash equals to u dash, and then this u dash we have assumed as v, new variable, and then y double dash is equals to u double dash, or you can say it's v dash because u dash is v. So this is your system. First is du over dx equals to v. So this is like your f1 x uv, and then this is your v dash, and this v dash like we have taken this 4y to the right, cos t minus 4y, and then y equals to u, so you will have cos t minus 4u, and this cos t minus 4u becomes your f2. This becomes your f2 x u v, and this becomes your f1 x u v, and this one is equals to v, and this one is cos t minus 4u, and then initial values like u naught is equals to 1 and v naught is equals to 1, as y dash is given 0, sorry it's 0. So y dash of x naught is 0 and x naught is here 0. And h is also given here in the problem 0.2. So since we have to use Taylor-Series method of fourth order, so fourth order means you have to consider all the terms up to h raised to power 4 and neglect other terms of the Taylor series expansion of u xi plus 1, and then you will get this as an expression u xi plus 1 is equals to ui plus h ui dash plus h square ui double dash h cubes upon 6 ui triple dash and h4 upon 24 ui fourth derivative. At here I means we are differentiating four times with respect to t, and then we are calculating value at you can say ti. If x is t, so you can say xi is actually here ti. So first you substitute the value of h is because h is given 0.2, so h is 0.2, h square upon 2 will give you this, h cube upon 6 will give you this, and then similarly you write fourth order Taylor series method for v variable also, like you will get the same as for u, you will get for v, and again you will substitute the value of h, h square, h cube, h4. So after substituting the value of h, we have to substitute the value of ui, u dash, ui double dash, ui triple dash, ui fourth dash at the point ti. Similarly for vi also. So first we identify what is our u dash. So as per the given second order differential equation, we have created this as a system of first order differential equation. So here our u dash is u and v dash is cos t minus 4u. So now if I want to know what is the value of u dash at I, so it means I want to know that u dash at not x. Here actually they have taken t. So at ti, but ti is actually initially it is 0. So like u dash at 0 we have to calculate. So u dash of 0, if this part you can say that it is actually equal to v of 0. And what is v of 0? V of 0 is given as 0. So it means u dash or ui dash of 0 you will get 0. You can see here. Okay, and then we required like how calculate v I dash. It means v dash at ti, and it means v dash at 0. So what is v dash? V dash is actually this cos t minus 4u. It means like cos 0 minus 4 of u0. And what is the u0 value? U0 value is 1. So u0 value is 1. You can see that u0 is 1. So and cos 0 is 1. So 1 minus 4 and minus 3. So this is like the value of v dash at 0. Now to calculate the value of, because second derivative also required and third derivative and fourth derivative, so we differentiate this. So what is u double dash? It is equals to v dash, and v dash equals to this. It means u double dash is actually equal to cos t minus 4u. Then what is v double dash? We differentiate this with respect to t one more time. We will get cos t is minus sin t and minus 4 u dash, and u dash is actually v. So you substitute all these value and you will get the expression of v double dash also. Then you calculate u triple dash. U triple dash is equals to, because u double dash is v dash, so triple dash is v double dash, and then v double dash value substitute from here. Then you again differentiate it one more time. You will get this, and then fourth time differentiation is this one, and then you again differentiate it, you will get this one. And then you substitute the now you calculate for I equal to 0, u naught equal to 1, v naught equal to 0, t naught equal to 1. These two values we have already calculated. Now we require the value of second derivative at 0. So second derivative at 0 is equals to v naught at x0, and v naught of x0 is actually minus 3. So this is the value of second derivative of u at 0. Now the second derivative of v at 0, second derivative of v at 0 is equal to this one. So if I substitute t equal to 0, sine 0 will be 0, and you will get minus 4 of u dash 0. And what is the value of u dash 0? It is 0. So finally v double dash is 0. Now u not triple dash 0, u triple dash 0 is actually v double dash 0. And what is the value of v double dash 0? From here we have v double dash 0 is 0, so it is 0. Now v naught triple dash is actually equal to this one, and then we substitute here t equal to 0, so you will get a cos of 0 minus 1 minus 4 of u double dash 0, and u double dash of 0 equal to minus 3, so minus 4 into minus 3 plus 12, and finally 11. And then u fourth derivative at 0 equals to v naught triple dash at 0, v naught triple dash is 11, so this is 11. And then v naught fourth derivative, v naught fourth derivative here you can see, and if I substitute t equal to 0, this will be 0, and you have with you only minus 4 of u triple dash 0. And what is the value of u triple dash 0? U triple dash value is 0, so here one dash is missing, so it is 0. So now you have all the values of uh, derivatives of u up to fourth order at the point t equal to 0, and then you substitute all the value here, and then you will get the first approximation, or you will get the value of y at zero point 0.2 like this. Similarly, value of y dash at this. Then you repeat this iteration for for I equal to 1, and then here everywhere you substitute t1, and then you will get all these values, and this is the value of u and v. So this is the value we obtained from the numerical solution. This is, and here we are calculating using the exact solution given in the question. This in this question, this is the exact solution is given: 2 cos t plus 3 cos t by 3. So if I substitute t equal to zero point 0.2 and t equal to 0.4, I will get the value of y0 and y 0.4 and y 0.2. And if I differentiate it one more time, like y dash of t I calculate, because here y dash is also required. So if from this exact solution, if I differentiate this with respect to t, then I will get y dash t, and then I substitute one time t equal to zero point 0.2 and second time t equal to 0.4. So I will get these four values. So these are the exact values we are getting from the exact solution. And then we compare the exact value with the approximated value. So this u1 is actually this one. This is 0.90940 So if I substitute here this one, and this is the exact, so this is the error. The magnitude of error in u1, the magnitude of error in v1, and like this. And then we have to solve the same problem with the help of Runge-Kutta method, and this is already discussed with you, so you should try this. So I am stopping here. Tomorrow we will discuss this multi-step method and this predictor and corrector method. So This we will discuss in the next class. Now I will take the attendance. So 1,
Present, sir.
2,
Present, sir.
3, 4,
Four present.
5, 6, 7, 8,
Present, sir.
9,
Present,
9,
sir.
7 and 9 present, 10, 11, 12,
Yes, sir.
12,
Yes, sir.
13, 12. Are you there?
Present, sir. Yes, sir. Yes.
Okay, 12%, 13, 14,
Present, sir.
15,
15%, sir.
14%, 15, 15 also
15%, sir.
present, 16,
14 also
16,
present. Sir, 10 present,
14,
sir.
15%, 16,
Sir, 10 present, sir.
17,
Present, sir.
18,
Yes, sir. Present.
19,
19 present, sir.
20,
Present, sir. Present, sir.
21,
Present, sir.
20%, 20, 21 also present, 22,
Sir, roll number
Present,
11.
sir. Sir, 10 present, sir.
Sir, roll number 11.
roll number 10 and 11 also present, 22
Yes.
also present, 23, 24,
Present, sir.
24%, 25,
Present, sir.
25%, 26,
Present, sir.
26, 27,
Yes, sir.
28,
28 present, sir.
29,
29 present, sir.
29%, 30,
30 present, sir.
31, 32,
32 present.
32%, 33,
33 present, sir.
33%, 34,
Present, sir.
34%, 35, 36,
Present, sir.
36%, 37,
Present, sir.
38,
38, sir.
39,